noisy tensors in machine learning too.
Yes.
So,
yes.
Right.
It's a potpourri, but not potpourri. Okay, so I'm going to start with something very applied. So for the first half hour, I'm going to describe this joint work. Dan Larimore is here at Boulder, but this was done when he and all these people were postdocs at the Santa Fe Institute. That's Ellie Power. She's an anthropologist who spent 2 years living in southern India, getting to know people in a couple of different villages. That's Katerina Dubako, now at Max Planck. She's a statistical physicist. That's me. And so yesterday, I described this kind of Poisson matrix factorization process. So, oh, and by the way, let me say two things. First of all, for those of you watching this at home, the slides are also on my webpage. Secondly, let me again remind you, for those of you here in the studio audience, please interrupt me at any time if I say something that you're not sure what I mean, or if I use unfamiliar notation, and so on. So again, the idea is that if you have some box of numbers which are non-negative integers, many of which are small, and you think that there's some underlying ground truth, like a low-rank tensor, but you think that these numbers have come through some kind of noisy process, either due to the imperfections of measuring things in the real world or because of actual random events in the real world, then you might think that these observed numbers are this low-rank tensor where each entry has been run through a Poisson distribution, which generates non-negative integers, where the means of those Poissons are given by the low-rank tensor. And if you think that, which, this may or may not have anything to do with reality, but if you believe that, then you have this optimization problem, try to find the low-rank tensor underlying these integers. So one application of this, but of course the word application is very rude, right? I mean, if people say, if you tell someone about your work and then they say, are there any applications? That's really, that's really just code for, gee, that doesn't sound very interesting. Although it's also fun when, one mathematician is talking to another and one describes something, extremely pure and abstract, and then the other one says, are there any applications? Then they say, yes, you can solve this other very pure and abstract problem. Then some mathematicians will say, that's a really good application. Thank you. All right, anyway, this is a more applied application. So as you probably know, network theory is very popular right now. But a lot of network theory treats networks, social networks, biological networks, whatever, as graphs. And of course, then we get to do lots of beautiful graph theory. And for instance, I really enjoy random graphs of various kinds. But in terms of claiming that we're learning something about the world, there's something rather thin and impoverished about viewing a lot of these real world things as graphs for a lot of reasons, but one of them is that in the real world there are typically many different types of links. You could have different social relationships, you're friends with certain people, you're collaborators with certain people, you're married to certain people, you loan money to certain people, and so on, and we wouldn't want to just flatten all of these different relationships into a single binary relation and say, you're either linked or you're not. So what we were interested in was what some people call multi-layer graphs. Some people call them multiplex graphs. They're multi-something graphs. You can think of them as graphs where the edges are colored, or you can think of them as multiple graphs where I have the same vertex set, but different types of edges in different layers. I'm sure our organizers are negotiating with the construction crew about that. Okay, So now we might think that these different layers are related in some way. The most naive way is that they're simply correlated with each other, but maybe there's something else. Maybe they are explained by some common community structure, but that they're related to those communities in different ways. So here's what I mean by this. So here is kind of a traditional picture of a social network or a something network with two communities where we have denser connections within the communities than we do between the communities. And we would call this, depending on which scientific community we're in, assortative or homophilic, or a physicist would say ferromagnetic. But there might be a different type of relationship which is actually more likely between the two communities than within them. So, for instance, if we have a mostly heterosexual society, these could be marriages between men and women, or if we have economic relationships, these could be suppliers and consumers. So certain types of economic relationships are more likely to cross between those groups than to be in either group, and so on. And, you know what I'm going to say, if I simply flatten all of these into a single graph, I get a total mess, where if I then scrambled this up and asked you who's in what community, well, maybe the combination of these two types of links just blurs everything out and produces some graph where there would be very little signal. But if I showed you these two different things, then you would say, there's a lot of interesting community structure here, and each of these types of links is fairly understandable. Moreover, if you knew that these links were disassortative and these links were assortative, then even though they're not correlated, if anything, they're anti-correlated, telling you about one of them would still help you predict the other one. Okay? So in that sense, these different layers are related. So what do we do? Well, now instead of an adjacency matrix like we would have in a graph, we now have a tensor, hence giving this talk this week here. And so I'm going to say that Aij is the, it could be 0 or 1, the presence of a link, but more generally, it could be the number of links. We could have multi-graphs from node I to node j in layer alpha, or if you like, the number of links of type alpha between vertex I and vertex j. And again, I'm going to, as I talked about yesterday, I'm going to pretend that these are Poisson with some underlying tensor as their means. And I'm going to adopt a particular decomposition here. So this is not quite saying, if you glance at this, you might think I was saying that this was a rank K tensor, but if you look more closely, you'll see it's a little bit more complicated than that. It's actually a rank K squared tensor, so what's going on? Well, here the idea is that, remember yesterday I was talking about topic models, and so I talked about a matrix where UIK was the relevance of document I to topic K. And there I had this model, this kind of traditional model, where I had connections between I and J, in that case, occurrences of a word J in document I to the extent that they were both relevant to a given topic. So I had K here and K there. But now I'm going to have UIK and VJL. You can think of this as the extent to which vertex I, person I, whatever it is, belongs to community K, and the extent to which J belongs to community L. And then this is a little matrix that says roughly how often do things in community K connect to things in community L with a link of type alpha. So this is what some people call a mixed membership model. In other words, you are allowed to, indeed encouraged to No problem. You're encouraged to belong to multiple communities to some extent, as we all do. And you might connect with someone else for a variety of different reasons. And all of those would contribute to the overall expected number of links between you. All right, so once we write this down, then it's not very hard to derive update equations analogous to the ones I derived yesterday with that same variational trick. Let's see. Yes, I just said all these things. Right. Anyway, never mind. But a couple things. These are actually directed links. So, this is not necessarily... it's not necessarily a symmetric matrix. So, so I can have links like people in this community are likely to loan money to people in that community and so on. Okay, anyway, so here is this thing about tensor factorization, and we've all heard these things, that tensor rank is NP complete. And so then here are equations. These are just more complicated versions of the equations I wrote yesterday. And so here is this thing that I called Q yesterday. It's our guess about to what extent a link between I and J is because I is in group K and J is in group L. And then these are these maximum likelihood update equations. So again, we iterate until we reach some kind of fixed point. That's a local maximum. No guarantees it's the global maximum. And again, this is just trying to find what we would call a point estimate of these parameters. And as someone interested in Bayesian, it seems to be moving around. It was, okay. Maybe it will get farther away now. As someone interested in Bayesian inference, I just want to comment that in general, I don't want to commit to single values of these parameters. I would much rather know what their distribution is given the data. But here, this type of algorithm is just trying to get a value of them. Okay, anyway, so what do we try to do? So what was the motivation here? So Ellie, the anthropologist, wanted to know, well, how are these different layers related to each other? So for instance, if I tell you who you ask to watch your kids, does that help me predict what the financial relationships will be, and vice versa? So she measured. Well, I'll tell you about this. So in machine learning, we often do this thing where we take a bunch of data and we arbitrarily just hide 10 or 20% of it from the algorithm. So we separate it into what we call a training set and a test set. We show the algorithm the training data and then ask it to fill in this test data. And if it can do that well, then we think we've learned something about the data set. That's a kind of standard practice, often called cross-validation. Blah, blah, blah. I don't really want to tell you some of these things. Oh, I do want to say, I don't know if this is the sort of thing you're interested in, but kind of from a philosophy of science point of view, we can ask, well, what is the best model? What is, how do we figure out what the right model of data is? And, having been raised as a physicist, I think this is interesting because in most of physics, the models are so simple and clean and the data is so plentiful that it's sort of blindingly obvious when you've got the model right, at least until then you move on to the next range of length and time and energy where that physical model breaks down, and then you need to know, then you need a new one. But for instance, it's very clear that the planets move more like ellipses than like circles, right? Except for Mercury, which precesses because of general relativity. But anyway, Kepler didn't have to do any statistics when saying, aha, they're ellipses. People at CERN do need to do statistics because they're interested in rare events involving elementary particles. But it's usually clear what the right model is. in this setting, this model isn't true, right? This model is a rough attempt to capture the dependencies in this box of numbers. We don't actually believe this is what's happening. And so here, the best model is really application dependent. It's like, well, what do you want to do? Do you want to fill in a particular kind of missing data? The best model to do that might be this with these parameters. But the best model might even depend on what kind of data is missing. So for instance, if I remove or hide from you a kind of random sprinkling of entries throughout the entire tensor, an equal fraction of links in every layer, and that's what I want you to fill in, the best model for that will have some parameters. But instead, if I say carve out a block of the tensor or remove most of one layer and show you all the other layers, the best model for that might be different. So, so I think it's interesting that in this case, the right model really is application dependent, and it should be. You can think about that while the drill is, okay. All right, anyway, so what happened? So here were Ellie's data had 2 Indian villages, about 400 people, lots of different edges, and she measured through her fieldwork 12 different kinds of social relationships. And, I should also mention here that, of course, her fieldwork was infinitely richer than collecting this tensor, right? It was notebook after notebook of real human conversations and interviews. This is just the data that she could hand to me after taking that massive amount of human interaction, putting it through a very low bandwidth channel, and giving me a box of integers. So professionally, that's what I'm capable of handling. As an intellectual, of course, I'm interested in all the rest of it as well. Okay, anyway, what happened? Well, this thing called the AUC is a kind of general measure of these prediction algorithms. And what this showed us was that here are all these different layers, and here is how learning more layers improved the prediction value. And I won't belabor this, but we found out, for instance, that it really helps to know who you ask for advice about important life decisions. This was one of the most informative layers about all the others, which was fun. We looked at another multi-layer network from Dan Larimore's work with Caroline Buckee at the Harvard School of Health. And this was from variants of a gene from malaria. So malaria is really nasty, tricky stuff. I didn't really know about this. You probably have heard about the reason HIV is able to evade your immune system is that it's constantly changing the protein sheath on the outside of the virus. So it's hard for your immune system to nail it down and build a response. Malaria does something a bit similar. So the parasite gets into your bloodstream, and it doesn't want to circulate because then it will be filtered out by your spleen. I didn't actually remember from high school what the spleen does, but anyway, that's one of the things it would do. So the malaria parasite sticks to the inside wall of your bloodstream and reproduces in a certain way. But in order to stick there, it is constant and not have your immune system say, what is this foreign body here? Let's attack it. It, a bit like HIV, is constantly changing the proteins, the sticky proteins it's using to do that. Very clever, nasty stuff. And so it has this amino acid chain that is coded for by its genome, and it's constantly altering at different loci along this string some of these amino acid groups. And so one of the things that Dan did was collect this multi-layer network where we can define 9 different types of links based on similarity at this locus or that locus or that locus. And then what happened here was that we did not find any common community structure. In other words, this didn't work. Telling me about the similarity at one locus did not help me predict similarity at a different locus. And well, some of the referees said, well, this is bad. This is a good reason to reject your paper. And we're like, no, this is cool. This somehow suggests that the virus that the parasite is being clever. And they were like, okay. So anyway, it got accepted. Okay, so that's all I wanted to say about that. Oh, look, a shameless plug for my book. Okay, and now I'm going to switch to the board. All right. The up button?
Yeah.
Okay. Any questions about that little applied experience I had? I mean, yes?
So how much did your models vary based on like the way you're training data streams? Like what kind of ways did you vary how you choose?
The question was, how did our models vary? How did we choose? What did you say?
Choose your training data.
Oh, how do we choose our training data? So we tried a couple of different things, a little bit like I mentioned a moment ago. So we tried one task where I hide most of one layer from you. I tell you all the other layers, and I try to fill in that layer. We tried various other tasks, like I show you a handful of layers and ask you to fill in a different layer, and then we vary which handful I show you. So, we were curious, for instance, which groups of 3 layers are good at predicting the other 9 out of 12. And I think the goal here was to understand, like, I think from the anthropological point of view, Ellie asked people all these different questions, like, again, who would you ask for advice, who would you ask for a job, who would you ask for a loan, and so on. Well, presumably these questions are not totally independent from each other, right? So for instance, if there's somebody who you often work for, you might ask them for temporary employment, and you might also ask them for a loan of money. So the goal here was to try to figure out, well, kind of which are the independent layers, if you will, that are roughly independent of each other, but if you know all of those, you get many of the rest of them. And but we did also try this other task where we just remove a random sprinkling of edges roughly evenly from the whole thing. I mean, something I didn't tell you is, like, how did we choose the number of groups? That's an issue in in yesterday's topic models as well. How do we choose the number of topics? If you are going to try to approximate a matrix or a tensor with something low rank, how do you choose the rank? And like this is an issue even in good old-fashioned singular value decomposition. If you look at a real noisy matrix, it'll have a few large singular values, and then they'll start to fall off. And at some point you'll say, oh, the rest is noise. But where do you decide to do that? And most of the time in practice, people use very hand-wavy, kludgy criteria to say, oh, these are the important singular values, and the rest I'll label as noise. And if you make particular assumptions about the nature of the noise, then maybe you can make a more mathematically principled decision. But mostly people say, there's even this thing called the elbow method. I'm not kidding. Where people say, oh, it's kind of curving down. I think I'll stop there. So anyway, there was another question. Yeah.
I was just going to ask, there's a step in which taking real information like the stories of people gets coded into these numbers.
Right.
How much feedback can we give to people creating these data on how to create good coding systems to make the data you want to process best?
The question was, how do we go from things like all these conversations to this data, and how do we code that in a good way? And
what do they need to know from us, the statistician, mathematician?
I see. So like what should statisticians and mathematicians tell social scientists about how to code this data as well as possible? I mean, the good news is they think about this a lot. And so in addition to 2 years worth of conversations with people, I think for this particular data set, if I understand correctly, what Ellie did was say, okay, here's a little worksheet. Please list up to 4 people that you would ask for advice. Please list up to 4 people, that you would ask to watch your kids if they were available.
There's also numeric estimates collected.
Yeah. So I mean, I think that kind of quote unquote nomination process was a very small but specific part of her field work. Yeah. Yes.
To those 2 villages, were they linked in the map or real life?
Yes, so you saw, I didn't say this out loud, but you saw on one of the slides that one of the 2 villages is, I'm sorry. Right, there were 2 villages that were not linked strongly. One of them was composed of 2, as we say, hamlets. And there were connections between those 2, but there was also a fair amount of community structure. One of the interesting things, I mean, she also knows like where people live geographically. So one of the interesting things is that some of these social relationships were very local, strongly correlated with are you close neighbors or not, and in particular, are you in the same hamlet, the sub-villages, and others were more global. Any other questions? Yes?
So you were talking a lot about the layers that you're looking at based on the different kinds of aspects of social networks, let's say. Could you obtain similar kinds of information if you looked at different kinds of layers, like you individualized specific, say, community leaders, you looked at the slice of their maybe multi-layered bit, where they interact economically, advice, and the well-being and stuff like this, but for particular individuals. So it's sort of a different kind of slice from that.
So the question is, if we focus on particular individuals and look at their relationships, can we learn specific things? I mean, you could focus on the community leaders, but that's also a small number of people.
Yeah.
And the number of vertices was only about 700 to begin with. So, I mean, one kind of side note is that I think culturally this is very different from a lot of the social network research we hear about that focuses on huge online social networks, for instance. So this was, if you like, a small but rich data set as opposed to a big but kind of flat data set like we tend to get from Facebook, Twitter, and all that. One of the interesting things in India, for instance, is social caste. And as you can imagine, there are strong signals there about social caste, and because of these unfortunate taboos about marrying between castes and their correlation with economic position and so on. And so, we did also look at various measures of influence and importance, and because some of these links presumably might be directed up from lower status individuals to higher status individuals or the other way, and so you can try to infer that and so on. So we did a lot of fun things, but all right. So that was practice broadly defined. Now I want to go back to some theory. Good. And oops, let's see. So, okay. Good. So this is the first time I've tried to present this material. I hope it goes well. Just, again, please ask me questions. I want to start out by describing a physical model, which you should know about if you've never heard of it before. The most basic version of this model is often called the Ising model, and the vanilla Ising model works like this. I have a set of spins where I ranges from 1 to n, and these spins are either +1 or -1, and we imagine these being little atoms whose magnetic field is oriented north or south. And then I have an energy function of a configuration of these spins. So I have 2 to the n possible states or configurations. And I have an energy, which physicists call the Hamiltonian. Yes, that's the same Hamilton, not the one with the musical, the other one. There's actually a really good YouTube where there's a parody of the musical about Alexander Hamilton, about William Rowan Hamilton. I will not impose my singing voice on you. So this energy function might be this: the sum over all neighboring pairs of atoms in some graph. In physics, we are often interested in this sort of graph. And then I would take the product of these spins, and then because low energy states are kind of more attractive in physics, I would put a minus sign there. And so what does this energy do? Well, the energy is lower when lots of neighboring pairs are of the same sign. This is called ferromagnetic, as in ferro for iron. And if I then sample from this thing called the Boltzmann distribution, which I mentioned yesterday, how would this work? I would have a probability distribution over configurations S, which are, specifying S sub I for all I, and it would be proportional to this thing. So I normalize. I'm writing this beta here just for your cultural enrichment. Beta here is just 1 over the temperature. I think yesterday I actually wrote it as over the temperature instead of times beta. And so if you sample from this distribution, you get all kinds of interesting behavior. And equilibrium statistical physics really is all about what do typical states drawn from this distribution look like. And we get nice phase transitions, for instance, where on the 2-dimensional grid, in the limit where the dimensions of the lattice are large, you can put it on a torus if you like, then when the temperature is sufficiently low, I will tend to get a typical state will be a majority +1 or -1, but one or the other, with small islands of the opposite state. And this corresponds to this material really being magnetized, so that, say, at a particular temperature, perhaps 80% of the atoms are all lined up together, and so there's a strong overall magnetic field. As I raise the temperature, these islands kind of grow, and then at a particular critical temperature, which is different on the 2-dimensional lattice or the 3-dimensional lattice and so on, the islands merge, and I can no longer say which are the islands and which are the sea, and then I have this kind of interpenetrating pluses and minuses, and at large scales I have an equal number of pluses and minuses, and at that point the material is no longer magnetized. So this is called the Curie temperature, and it actually happens for real blocks of iron. So there's lots of interesting physics here. Now, good. So what else did I want to tell you about this? Oh, it turns out that even the ancients knew that magnets got weaker when you heated them up. Newton says that the magnetic, with a CK, magnetic bodies lose their virtue V-E-R-T-E-U-E, wait, yeah, virtue, when made red hot. But I don't think he realized that there's a critical temperature at which the magnetic field quite suddenly just goes to zero. And in the two-dimensional model, there's in fact an exact solution, which is very beautiful, but I do not have time to tell you about it. But it is related to the fact that you can compute the permanent of planar graphs. The permanent of the adjacency matrix of planar graphs. But anyways, so the magnetic field goes like this at this critical value of the temperature. There was a question back there.
So what does that two-dimensional graph represent? Just like a spatial representation of just atoms?
Yes, so each vertex here is one of these indices, and at each vertex of this graph, which in this case is just a lattice, I have one of these variables s sub I, and this sum, the interactions are just between neighboring pairs. So if you like, I should have written that if I have a graph with edges E.
Each vertex represents an atom?
Each vertex represents a single atom in a material, in this case, a material in flatland. For a real three-dimensional one, I might have, say, a cubic lattice. And then each of these atoms has a spin, which can be +1 or -1, and interacts with its neighbors according to this energy. Yeah. And I think, the nice thing about, for equilibrium physics, defining a model means defining this energy function. This doesn't really tell you anything about the dynamics, about how things flip, and so on. But at equilibrium, in some sense, what we really care about is this probability distribution. Okay. So this is all lovely stuff. But what I want to tell you about now is a generalization of the Ising model, which is called the Sherrington-Kirkpatrick model. So first of all, let me put a coefficient here, Jij, and we would call this, maybe I shouldn't call it Jij, but that's what it's usually called. And we would call this the coupling between I and J. And notice that if it's positive, it encourages I and J to line up together. If it's negative, then because of this minus sign here, which is there, partly for historical reasons, then the energy would be smaller if that pair were anti-aligned, which is what we would call an anti-ferromagnet. And there are, in fact, materials where the neighbors prefer to be aligned against each other. And now imagine that these Jijs are random. So imagine that they're chosen, say, from a Gaussian distribution with variance 1 and mean 0. And furthermore, imagine that all pairs interact. So if you like, I have a complete graph, but each edge now has this weight, this random weight on it. Okay. And okay, good. So this is called the Sherrington-Kirkpatrick model. And I'm not sure how much to tell you about kind of why it was invented and where it came from, but the idea is that some materials are very disordered. And originally the motivation, okay, I guess I'm going to tell you. Originally the motivation was to understand things like window glass. So if at an atomic level, window glass is not actually a perfect crystal, it's a much more amorphous jumble of where the atoms are, even though they're sort of held together in a rigid framework. And interestingly enough, silicon dioxide has its lowest energy state as a perfect crystal. But if you take a bunch of molten silicon dioxide and cool it down, it never finds that low energy state. it gets stuck for the age of the universe in this amorphous state, which means it's actually not at equilibrium, right? At equilibrium, if we cool it down, this says you will tend to prefer those low energy states. So it's an interesting kind of material which has gotten stuck in a part of its landscape, sort of, if you like, again, we're trying to minimize the energy, the kind of amorphous jumbled states are over here. Over here is a very low energy state, the perfect crystal that we'd like to find, but we get stuck here for an astronomical amount of time because in order to get over this high energy hump, that the probability of these states is exponentially small because of this factor. And so dynamically, it would be very hard to make this transition. More concretely, what I'm trying to say, for instance, is that there might be a couple of atoms sort of lined up in a little bit of crystal here, but over here they have a different orientation, over there they have a different orientation, and I would have to make, in order to get these to line up with each other, I would have to make the energy higher, I would have to make things worse before they got better, and that keeps it stuck. So as a kind of toy model of this sort of amorphous situation, people invented these things, which are called spin glasses. And as a, if you will, a toy model of the toy model, we imagine that rather than having a spatial structure like a grid where things interact with their neighbors, we'll let everybody interact with everybody else, but with a random weight. And so if you have, for instance, in this complete graph, you will have lots of triangles where these two want to be lined up with each other, but these two want to be, these two want to be lined up with each other, these two want to be lined up with each other, but these two want to be different. So we would have this kind of frustration, and this would create a bumpy energy landscape with lots of local optima in which to get stuck. All right. Now, suppose I want to compute what we would call the ground state energy, which is the minimum of this energy over all spins. Again, if we're at a non-zero temperature, then the states we find would be drawn from that Boltzmann distribution, but in particular we might like to ask, well, what is the lowest energy we can achieve? So what is the minimum over all possible configurations of this function, which, by the way, as you can see, is minus this bilinear form, but I want to minimize just over the +1, -1 choices. Okay. Notice that this function, this is a random variable because it depends on the choices of these random weights. So what I really mean is, what is the typical value of this, if there is a typical value, in the limit that n is large? And good. By the way, I am going to normalize this by a 1 over n. Okay. And let's think about roughly how this should scale. Well, and some of you know exactly where I'm going with this. If I take this matrix J, so again, J's entries are these independent Gaussians. Oh, sorry. J's entries are these independent Gaussians, and then what's the typical operator norm of J going to be? Somebody who didn't know this before. I have an n by n matrix where each entry is Gaussian with variance 1. What do you think the operator norm is roughly? If the entries were all 1, its operator norm would be n, but they're not. They're random. Any ideas? Well, if things are random, and if things would add up to n if they weren't random, what happens when they're random? Square root of n. Right. So you might guess that it's order square root of n, and if you know this story, you know in fact that we know exactly what it is in the limit that n gets large, then with high probability, anyway, with high probability, it's 2 root n plus a wee bit, right? In fact, we know much more than this. So the theory of these Gaussian random matrices is very rich. We know the entire spectrum, so we know the spectral density, and we know that it follows what people call the semicircle law. So this here is the density of eigenvalues in between -2 and +2 root n, and this goes back to Wigner, and there are lots of beautiful ways to prove this. And these Gaussian random matrices have lots of nice properties. In particular, if they're basis independent. If I rotate them on either side by any orthogonal matrix, they stay the same. There's one little tweak I need, which is, strictly speaking, on their diagonal, I have to make the variance 2. Yes?
What does this J matrix represent?
Well, in this physical model, it represents the interactions between these pairs of atoms in this spin glass model. But at the moment, I just want you to think of it as a random matrix. Okay, it's a matrix whose entries are independent Gaussians with variance 1. Josh? I'm sorry, the question was, what is J?
If it's easy to say, the actual statement of the semicircle is like, as n goes to infinity, a random eigenvalue is drawn from this distribution with probability 1 or something like that?
Yes, let's see. If you defined, first of all, I guess we should scale things by root n to make things simpler, and then we would define under that scaling a density of eigenvalues, and we would say that rho, let's see, okay.
It's not easy, we can talk about it after.
We would say that J, the number of eigenvalues of J such that lambda is inside a little interval x times root n, or root n times x plus dx. You know what I mean. Sorry. It's hard for me to do this on the fly. I think that looks about right, where rho is the square root of 4 minus x squared. And so this goes by the name of Wigner's semicircle law. Of course, it's a semi-ellipse, but anyway. Oh, sorry. 2 pi? I think 2 pi, yeah. Okay. And moreover, it's also true that the maximum eigenvalue with high probability is right at the top of the semicircle at 2 root n. Okay. Good. So random matrices are lovely, and I should mention that random matrices are one of these great areas where there are physics-style calculations, which are usually correct but often non-rigorous, and then there's a lovely interplay between that and the mathematical world of making them rigorous. Yes?
I I don't want to go off topic, but if it's a simple answer, if you scale up in the valence and you had a random 3 tensor, does it still connect to a sphere? And does that mean that the decrease in the volume is going to mean you see the effects less?
The question is, what if we go up to a 3 tensor here, and that's actually where I'm going in 5 minutes?
Then I'll wait.
And it's a great question. Okay. Anyway, good. So, going back to this model, it turns out that the typical value of this minimum is minus 0.73 times square root n. And this result also has a fantastic history. It was first calculated in a wildly non-rigorous way by a statistical physicist named Giorgio Parisi, who kind of began a whole field called replica symmetry and replica symmetry breaking, and you may have heard of some of these things. And then this was eventually made rigorous by Talleyrand, but the physics calculation of it was, using delightfully crazy techniques. And it took a long time to nail it down. But notice the difference between that and this, right? The point is that suppose that I was minimizing over the sphere where the norm of S is n, the norm squared is, right? Then I just told you what the answer would be, because then if I set S equal to that top eigenvector of J, it would have been minus 2 root n. So one interesting fact is the gap here, which is really due to the restriction that the entries of S be plus or minus 1. But stepping back from this a little bit, let me say a word about computational complexity. It might not surprise you that if rather than choosing these J's randomly, I allow an adversary to choose them, to cleverly design an example of a spin glass, then computing this minimum is NP hard, NP complete. The question of whether I can achieve an energy below a certain threshold is NP complete. And I could prove that if I wanted to take 5 more minutes, but it's not very hard to prove. And you can imagine that, well, this is a complicated function and I might require some kind of exhaustive search. But on the other hand, I can compute the operator norm of a matrix in polynomial time. Okay? So if you ask me this question for some fixed J, I might be nervous, but, because it might take me exponential time. But as a first cut, I could say, well, guess what? I can quickly compute a lower bound for you just by taking the operator norm of the matrix. And let me phrase this in a slightly more computer science-y way. If you came along to me and said that, you said, I claim that I have found a set of S's that achieve a particularly low energy. If I then look at the operator norm of J, I could say, I can refute your claim. And indeed, I can refute it in polynomial time. If your claim is too wild, if you claim that the energy is below root n times the operator norm, I can say you're just wrong. Now there might be a region in between here and here where it's hard to refute your claim. Okay? All right, so you see where I'm going with this? So there are, in other words, there are times when a problem is computationally hard, But if someone makes too extreme a claim about an optimization problem, then there might be a polynomial time refutation of it. A refutation which we can both find in polynomial time and confirm in polynomial time. Yes?
Yeah, so has anyone tried to understand this gap a little bit more? So like, for instance, look at like half integral solutions instead of plus minus one?
I haven't heard of that, but sorry, the question was, have people thought more about this gap and maybe things in between, such as, for instance, half integral solutions? I haven't heard of half integral solutions in this problem, but if, computer scientists have a general word for this. I guess lots of people have a general word for this. This is a relaxation. I am making an optimization problem less constrained. My less constrained version is easier, because if I'm minimizing over the entire sphere, then I can just use the spectrum of the matrix J. And this is a common practice in computer science, to get a bound on an optimization problem by finding a relaxed version of it, which we can solve in polynomial time. And and this is also common in linear programming, for instance, as I think I'm guessing you know. So if they're solving linear programs maximizing some linear function subject to a set of linear inequalities, if I restrict the vectors to have integer entries, this is NP hard. If I don't restrict them in that way, then it's in polynomial time. And then there are some special cases where I know that that even the relaxed problem has half integer solutions, so I'm not too far from a solution to the original discrete problem, and so on. Here, there's a lot of depth here, including the Grothendieck constant, and that's sort of sliding off what I know about this problem. Yeah. Yes?
This is a related question, I think, but what if you use like the L1 operator?
Yes, but I'm not sure if we know what that is. The question was, what about other norms, like the L1 operator norm? That is another good question, yes. Although here, well, let's see. There is this practice if I want a sparse vector of limiting the L1 norm, but here I'm interested in the corners of the hypercube, so it's more like the max norm, I guess, is what I would want.
You're saying some of the answer is
That's also true. Yeah, that's a different relaxation. Is if I optimized over the metric polytope, the n-dimensional octahedron. Yeah, Josh.
So you said with high probability, the operator norm is within a constant factor of the discrete optimization. Does the operator norm always give you a constant factor approximation in the worst case?
No, I don't think. The question was, does the operator norm always give you a constant factor approximation, that is one which is some multiplicative constant away from the true optimum? I think that you could probably come up with specific examples of matrices J for which that's not true, but it typically does in this random setting. Okay. All right. Good. So now that I'm going to switch to the right-hand side of the board. Good. So, by the way, one thing I want to show you is a quick proof of a slightly weaker bound. So let me remind you first of the Chernoff bound for sums of independent random variables, such as, so let's say that I have a bunch of independent things which are Gaussian with variance 1, or which are bounded by this distribution in a certain sense. Actually, I want all the moments to be bounded, but my canonical example will be, or they're uniform in plus or minus 1. So now if I have a random variable capital X, which is the sum of n independent psi i's, then I know that the probability that the absolute value of x is greater than t is at most 2 times e to the minus t squared over twice the total variance of all of these things, where the variance of each one is 1 and the variance of independent things is the sum of the variances. So this here is just n, if there are n of them. And this is a very handy bound. Now, there is also a matrix version. And this says, well, suppose that I have a matrix X. So now this is bold X. Okay. And there are lots of different ways that I might be interested in this, but I'm going to focus on a particular type of sum where I have, again, just numbers, psi I, but these are coefficients for some fixed matrices A sub I. So X is a random linear combination of a bunch of matrices A sub I. Then the analogous fact is that the probability that the operator norm of this is greater than some number t is at most twice the dimension of these matrices times e to the minus t squared over something very similar, but now instead of just the variance of these, so to make, for simplicity, let me say that now the psi I do have variance 1. What I put here is the operator norm of the expectation of the square of this matrix. And if you take this matrix and square it, and then take the expectation, the cross terms, where I have psi I times psi j, will all disappear because they're pairwise independent and have mean 0. And all that will be left is just the sum of the ai squareds, because the expectation of psi I squared is 1. Okay? So this is a nice bound to have. And yes, I will talk about tensors at some point. So now let's go back over to the left side of the board. And let's apply this. Sorry, right side of the board for a second. You know, when is this small? I mean, this is, you know, well, let's say that I want this to hold, I want this right-hand side to be something small, like 1 over n, or something like that, something tending to 0 as n goes to infinity. What this says is that whatever this norm is, t will typically be less than or equal to the square root of this thing, whatever it is, and then maybe times something like log n. Although I also have to deal with this log d. So I guess something like log n plus log d. Okay? Because then I put minus t squared, blah, 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 and this kills that, and this just makes the whole thing small. Okay. Well, if I do this here, what is left side of the board now? Saying that Jij is a Gaussian is the same as saying that J is a sum of psi ij's times the elementary matrix. I probably should have told you that I actually meant that Ji and Jij were the same. This was a random symmetric Gaussian matrix. So actually I mean this. So these things here are my A sub i's, where this, the I on the right side of the board is this pair I and J. And n, the number of terms in that sum is, well, sorry, it's n squared, or n choose 2. All right, so when I put all this together, what do I get? I get that with high probability, the operator norm is at most, well, if I take all of these and square them, I get roughly the identity matrix if I square them and then add them all up, right? So the norm is 1, and then I just get, wait, sorry, that's not true. Why are you nodding your heads? That's a total lie. When I square these and add them all up, at each I have n choices of j, such that eij times eji equals eii. So I get n times the identity. Good. So then what I get over here is, I'm sorry. This should have said the operator norm of all this. And the operator norm of n times the identity is n, so I get square root of n, which is what I wanted, times log n times some constant. All right. So this simple Chernoff bound gives us the truth with some log n slop. Okay. Good. Let's talk a wee bit about tensors before lunch. Okay. So first of all, one direction we could go in is increasing the arity and having, say, triples of spins interact. And then I would have a random Gaussian tensor. And then how would I get a spectral bound on my energy? Well, it's a little trickier now, as you all know. I could say, well, let me flatten J into something I will call J bar, which is an n by n squared matrix. We could do that, and then I would have on the left here S transpose, and on the right S tensor S. And we know that we're doing terrible violence here, right? We learned yesterday that the right diagrammatic way to view this would be to put J here and have 3 spokes coming off of it and put S on each one. That's the correct symmetric way to view this. In order to squeeze that into the world of linear algebra, we have to do this disgusting thing of putting 2 of the copies of S on one side and 1 on the other, and we know that this is living in sin and that there will be a terrible price to pay. When I relax this, well, I don't even know how to solve this relaxed version of the problem where I merely say S is a vector with norm 1. I have to do something even worse. I have to relax it to S tensor J some other vector V, which is an n squared dimensional vector, because I don't even know how to handle the constraint that the vector on the right is actually a tensor square of a vector. So I'm now relaxing in 2 senses. I'm relaxing from the hypercube to the sphere, and I'm saying that S squared is n, and V squared is n squared, and dear God, what have I done? I'll still get some bound, and it will have to do with the operator norm of this asymmetric matrix. And we do know things about the operator norm of an asymmetric matrix with Gaussian entries. It obeys a different the spectrum obeys a different distribution called the Marchenko-Pasteur distribution. But anyway, this is a thing we could do. Okay. Right side of the board. I want to, just to bring up another computer science problem, which, so you may be familiar, and maybe Josh already told you on Monday, or not, about Boolean satisfiability. where I have a bunch of variables which are 0 or 1, and then I have a bunch of clauses which say things like, I want x1 to be true, or x2 to be false, or x3 to be true. And I also want x2 to be true, or x7 to be false, or x39 to be false, and blah, 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 blah. And then I have 2 to the n possible choices of truth values for these variables, and the question is there any setting of them which satisfies the entire formula, which means satisfying each of these clauses? And this is indeed one of the original NP-complete problems. It's going to be easier for me to talk about a different problem which is actually closer to these models, which is called XOR set. So in XOR set, instead of saying this or that, we say this XOR that, which is the same as adding them up mod 2. And so really, instead of clauses, we should think of it as a set of equations, like blah, 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 x1 plus x2 plus x7 equals something. I could flip a coin and make it 0 or 1, and so on. Now, if I ask you, can you satisfy an entire set of equations like this, you know how to do that. Those are linear equations. So you could do that by Gaussian elimination mod 2. But things are actually more interesting if I say, well, I'm not asking you, can you satisfy all of them? Okay? Instead, I'm going to ask, can you satisfy, say, 3/4 of them? Okay? Exercise. You can always satisfy at least half of them. Okay, good. So if you want the names of things, this is max XOR sat. And now, in the spirit of this random model, I'm going to make up random cases. So I will have n variables, x sub I, where I ranges from 1 to n. And I'm going to have m clauses, where each one, I guess this is max 3 XOR sat, each one of them will be a random triple of variables, and the clause will assert that their sum mod 2 is something where that something is also chosen randomly. Okay? So I make up a whole stack of equations like this, and then I ask you, can you satisfy a fraction of them which is bounded above a half? This is, again, NP hard, NP complete. And what does this have to do with tensors? Well, let me change these x's to +1 or -1, so that I'm now asserting that the product of three things is either +1 or their product is -1. And now let me write down a tensor, which I'll call y, and this is either 0 if there's no clause involving that triple of variables, or it is, say, I'll call it z ijk, if indeed we are told that the product of these three variables is a particular z ijk. So this is, if you like, a sparse n by n by n tensor, where most entries are 0, a total of m entries. I guess we can include permutations here if you want, but m entries are uniformly +1 or -1. And now the question is, what is the, I guess, as about a computer science will now maximize things instead of minimizing the energy. What is the maximum over all +1, -1 arrangements of these variables of this trilinear form. Yij, xi, xj, xk. So you see what's going on? Whenever whenever a clause is satisfied, then the product here will be equal to zijk, but that will cancel this and I'll get 1 here. Okay? And so, for instance, if I can satisfy 3/4 of these, this maximum will be greater than or equal to 3/4 times m. Yes?
Gotcha.
Okay. All right. So here's what I want to show you one other model in a similar spirit, which I'm going to go back over to the left-hand side of the board, and which is called the spiked tensor model. And yes, I'm going to do all this by noon. Okay. Here is the spiked tensor model. And it is meant to be kind of inspired by what we said yesterday, where we think there's some ground truth, which is low rank, but that noise has been added to it. So the spiked tensor model goes like this. I just assume that yijk is some constant. So now this will have real valued entries. It's some constant times a rank 1 tensor, the outer product of some vector with itself, plus a bunch of Gaussian noise. So each entry here will be Gaussian with variance 1. And to actually complete the model, I will also tell you that these x's are uniformly random vectors whose entries are +1, -1. So in order to produce one of these things for you, I first flip n coins, choose a random vector, take the resulting rank 1 tensor, and then add Gaussian noise everywhere. Permutation symmetrically, I guess. And then I hand you that. I now challenge you. I could challenge you to do two things. One thing I want you to do is give me x, at least approximately. So I would like you to give me a vector with +1, -1 entries, which agrees with x at more than half the coordinates. Okay? If you do that, I will give you a cookie. The other task, which seems closely related that I might like to ask you to do, is distinguish this from a model where y is just noise. Okay? So here I tell you, guess what? I have either generated y in this way with a genuine vector hidden in it, or I've actually just given you a random Gaussian matrix, a random Gaussian tensor. I want you to tell me which one I did. Okay. Good. So here's the nice fact. In both these problems, where here I'm interested in the ratio of clauses per variable, and I will call that alpha. Okay, so this is like the density of these random formulas. Oh, by the way, I'm on the right side of the board now. Sorry, this is going to keep happening, but not for that much longer. Good. There is, as soon as alpha is much bigger than a constant, okay, it's easy to show that it is exponentially unlikely that you can satisfy any fraction of these clauses greater than a half. Okay, so this is a simple probabilistic method argument, just counting the expected number of such solutions. So this is the threshold where we can no longer, can't satisfy 1/2 plus epsilon times m of the clauses for any fixed epsilon bigger than 0. Okay? But when can I prove to you, probably, that you can't? Which is different from proving to you that you probably can't. You know what I'm saying? I mean, if you cook up a formula with a density where alpha is, say, n to the 1/2, that m scales as n to the 3/2, well, you probably can't satisfy this many clauses. But I want to actually then produce a proof for you about that instance, that set of equations, that verifies that you can't, which is a different and stronger demand. Okay? Well, you can do that using the operator norm of a flattened version of this tensor when alpha is n to the 3/2, and in general, if I have p here, where p is the number of variables or the arity of the tensor, that happens when we have n to the p over 2. The gap here is, if you will, it's the cost of flattening this tensor into a matrix. It's the cost of doing that on the left side of the board. And, you know, for instance, flattening an n by n by n by n tensor when p is 4 into an n squared by n squared matrix. And it's the cost of relaxing to putting an arbitrary n squared dimensional vector on either side, which is not actually the tensor product of two vectors, let alone the tensor product of two vectors with +1, -1 entries. So here we know that there are polynomial time algorithms because we can do linear algebra in polynomial time. In between, we believe that there aren't, but we don't know. Okay. So in between, we believe that it is typically exponentially hard to prove to you that we cannot, in fact, satisfy, say, 3/4. Over here, left side of the board, we have a very similar thing. When lambda scales as n to the minus p minus 1 over 2, so if lambda is much bigger than that, lambda is kind of the signal to noise ratio here, right? It's the strength of the signal part of this. When lambda is bigger than that, it is what I will call information theoretically possible to do two things. One is to tell with high probability whether there is the signal there, and also to recover x approximately. To recover x and distinguish between this model and this model. But we don't know of polynomial time algorithms until lambda is much larger, which is n to the minus p over 4. And again, this is with arity p, where y is lambda x tensor to the p plus an arity p noise matrix. At this point, we have polynomial time algorithms. And in between, we think it's exponentially hard. These two are the same when p equals 2, if your blood sugar isn't too low to notice that. That's because for matrices, there is no gap between what we can do information theoretically with exponential time and what we can do in polynomial time, because for matrices, at least in this setting, where all of the entries of x are plus and minus 1, PCA, principal component analysis, just finding the dominant eigenvector of the matrix, works. It doesn't work quite optimally in the following sense. So, in fact, there the threshold turns out to be 1. 1 times root n. If you graph, so if you look at the dominant eigenvector and scale it and then take its inner product with the true underlying vector, that's like a measure of accuracy, right? PCA does this, and kind of optimum Bayesian inference, where you look at all 2 to the n vectors, which takes you 2 to the n time, and you figure out, what the most likely one is, that would look like that. It achieves a slightly better accuracy, but its threshold is the same. But that's for p equals 2, when this is just a matrix. Once we have a tensor, then we have this gap between these 2 different powers of n, where optimal Bayesian inference does that, and these polynomial time algorithms do that. And in between here, we think that it is hard. Physically, we think the reason it's hard is the same reason that window glass is not a perfect crystal. In other words, we think it's hard because if you actually looked at the landscape of all possible x's, where you could define the energy as minus the log of the probability or something like that, then you would have a kind of big amorphous blob here of x's that are not correlated with the true underlying x. And over here, you have the x's that are very close, the exponentially small fraction of them that are close to the true underlying x. And in this regime, we believe that there is this energy barrier separating these 2. So we think if you did a Monte Carlo algorithm or any algorithm that did some kind of local search, it would get stuck in here for an exponential amount of time. So there's this physics picture. There's our best known polynomial time algorithms. There's the conjecture that in between there's no polynomial time algorithm. And of course, we couldn't ever actually prove that without proving that P and NP are different, because if P and NP are the same, this whole thing is solvable in polynomial time. We could hope to prove that large classes of algorithms don't work in this regime. So we could hope to prove, for instance, what I was just alluding to, that if we did a Monte Carlo algorithm where I start with a particular x and I consider flipping individual coordinates from +1 to -1, and I do that with some probability based on how close that would get me, how much that would reduce the noise, that algorithm would be stuck for exponential time. So that's a well-defined conjecture that we could hope to prove with some clever probability and combinatorics. So I will stop there, but I really like the fact that the gap appears to be exactly due to the fact that we don't have linear algebra for tensors, that we don't have a good notion of eigenvalues and eigenvectors for tensors. If we flatten things, don't you really feel like we're like the creatures in Flatland, that, these beautiful 3- and 4-dimensional creatures are passing through, giving us these incomprehensible blobs appearing and disappearing, right? And it's the same thing. In order to get a polynomial time algorithm, we have to take these beautiful symmetric tensors that are native to these high-dimensional spaces and squash them so that we can see them and put some things on the left and some things on the right, and that just costs an enormous amount. So I'll stop there. Yes.
So I just want to clarify here, when you were talking about at that bound, you can't prove that there's no solution. There is no solution to have that many clauses.
Right. So what I was saying is that when the density is of of this system is large enough, when the ratio of clauses to variables is large enough, it is true with high probability that there is an ironclad proof that that system of equations I cannot satisfy more than about half of the clauses. I know that's a bit convoluted, right? As soon as the density is bigger than a constant, it is true with high probability that I can't solve more than half the clauses, and it's not hard to prove that statement that I just made. But if you want, you know, in computer science we often call it a certificate, or Josh called it a witness, right? I want to know, when does it become easy to provide a witness for that system of equations, that fixed system of equations, that I cannot satisfy much more than half the clauses? That doesn't become easy until I get up to this density. Is that clear? It's like, I love random graphs and the problem of when is a random graph colorable with 3 colors so that no 2 neighbors have the same color. This is one of my favorite questions. So there is a density at which you can show most random graphs with this average degree or more are probably not 3 colorable. But if I actually generate a random graph above that density here means the average degree or the ratio of edges to vertices, well, you're looking at it now and you'd like to know, gee, how can I tell if this graph is not 3 colorable? So when is there a proof of that, which does not involve exhaustive search in exponential time? Well, there are lovely spectral proofs that sometimes show you that a graph is not 3 colorable. For instance, if you think about it, exercise. If a graph is 3 colorable, its adjacency matrix has an eigenvalue less than or equal to -0.5. Hint. Here are 3 unit vectors where the inner product between each pair is -0.5. Okay? Now, this is not an if and only if, right? It could well be that a graph is not 3 colorable, but it does have an eigenvalue less than -0.5. Okay. But if it doesn't have an eigenvalue less than -0.5, or less than or equal to -0.5, that is a proof which is available for some graphs that it is not 3 colorable. And it's a proof which does not require you to look through the roughly 3 to the n possible colorings. So that type of proof becomes available to you for random graphs most of the time when they're dense enough. So there's one density at which they're probably not 3 colorable. There's a larger density at which it becomes easy to prove that they are not 3 colorable. There was another question back there.
Yeah, so I guess there's approaches in machine learning to maybe model themselves after some of these types of ideas from statistical physics. Is anything you said today going to be applied to that realm, or is these ideas on the side there?
The question was, are these ideas applicable to machine learning? Yes, I mean, this is, so I think the more general machine learning question would be, instead of, I'm stepping over to the left side of the board now, instead of a rank 1 tensor being the underlying thing, there would be, say, a rank R tensor. And, you know, I also kind of chose this symmetric version for simplicity. But in general, you would have x, y, and z here for 3 different vectors, which might have different lengths because your tensor might be n by m by t or something instead of n by n. And so then, I mean, this problem many people call this problem tensor PCA, even though that's kind of a lie because we can't really do PCA here. And so the claim here is that if the signal-to-noise ratio is large enough, then if you flatten this tensor into a matrix and look at its eigenvectors, you do learn something about these vectors. So Andrea Montanari and Siwang Oh, I hope I'm getting that right, have what they call tensor unfolding. So they basically say, let's say I have an arity 4 tensor, start by flattening it with 2 indices on the left and 2 indices on the right. If you believe, say, that this is roughly x tensor y tensor z tensor w for 4 vectors, well, then the left singular vector shouldn't be too far from x tensor y, and the right singular vector shouldn't be too far from z tensor w. Well, what they do is they say, well, take the left singular vector, it's say an n squared dimensional vector, now write it as a matrix, and look at its singular vectors. And its left singular vector, the dominant one, shouldn't be too far from x, and its right shouldn't be too far from y. So they have this proposed method of kind of iteratively breaking the tensor down into smaller matrices, and indeed we know now that this works here, assuming the noise is Gaussian. So that's a case where it's a pretty practical algorithm. I mean, you could try this out. It's a theory paper, and I don't know if this has actually been used in the world, but it could be. And as long as the variance of the noise is not too large, we have a theorem that it would learn something. So, yes, I think these are real algorithms. I mean, I think there's a cultural difference, right? So in machine learning, you have a goal, and by all means, throw the kitchen sink at that goal. And so in practice, people use all kinds of complicated algorithms that would be very hard for us to analyze theoretically. I think partly because I like physics, where everything is supposed to be as simple as possible, and partly because I like theoretical computer science, where, well, the same thing is true. I like studying simple algorithms where we can actually prove something about their strengths and weaknesses. But I think that those simple algorithms then are often useful in real data sets, or at least are good ingredients of perhaps more complicated machines or portfolios of algorithms that would be useful in real data sets. So, yes. And, okay.
No, one thing.
I just want to see if there were any other questions or if you're hungry.
Yeah, I was going to say maybe we should break for lunch.
Okay. All right. Thank you very much.